the recorder started, and we're gonna have a pretty, I think it's gonna be a pretty solid lecture today because we're gonna talk about Dijkstra's algorithm. I'm not sure where Iraj is in terms of Dijkstra's algorithm because I know he usually covers Dijkstra's algorithm in CISP 430, but I'm not sure whether he has started on it yet. Not yet. Okay. All right. So that's fine. So the way I do Dijkstra's algorithm is a little bit different from the way Iraj does his. So you have to remember, which class is which class, and don't use the wrong algorithm because they are similar but not exactly the same. So the way I do Dijkstra's algorithm is it can find the shortest path of every single vertex to a destination. It doesn't need just one single destination. You can have multiple destinations. So it's kind of special. It's kind of cool that way compared to the usual Dijkstra's algorithm that you can find on Wikipedia. So what I'll do is to give you guys a mental picture of why this is useful. Why do I want to have an algorithm that finds the shortest path from every single vertex to all the quote unquote destinations? First of all, why do we have multiple destinations? Okay, that's the first question that I will answer. And then the second one is, what is a vertex representing in one of the applications of this kind of graph representation where there are multiple destinations? So the mental picture I want you to get is this. Okay, so I'm gonna go over there, and I'm not sure whether it is still called Six Flags or not, but last time it was still called Six Flags. All right, so it's a theme park, as you already know, and we want to look up um, the map of Six Flags. Yeah, that one is pretty good. All right, where's the map? Mm, okay, official park map. Okay, where's the map? They showed a map in the previous page and now it's gone. What is going on here? Hmm? Oh, that's just parking. Ah, okay. Park maps, past park maps. Visit the park's website for this season's official park map. No, it's not for parking. It is the park map. It's supposed to be for the whole thing. Uh, okay, this is for parking, picture pass, fast lane, parking. Where's the actual general map? Ugh, and they expect people to go. Okay, that's fine. We'll just take a look at this map here. So imagine that you are taking a whole bunch of second graders. Okay, you're the chaperone, and there's a whole bunch of second graders going with you to Six Flags. So what is the most common request when you have second graders going to a field trip like this? Exactly. I need to go to the bathroom. Okay. So you definitely want to find the shortest path in that case because otherwise you might end up with a mess to clean up. So you definitely want to get the bathroom, get to the closest bathroom. So you would hope, okay, I cannot confirm that, but you would hope that with a theme park of this scale, they would have multiple bathrooms and not just one single bathroom at the entrance of the whole theme park. That would definitely be bad because in that case, the park is gonna smell like toilet, and we don't want that. Does that make sense? Okay. So every bathroom is a quote unquote destination. So the algorithm that I'm going to talk about is going to be able to find the shortest route, or I should say, the route to the closest bathroom from every intersection of the theme park. Is that okay? Does everybody understand, what this algorithm can help generate? So that means, once you run this algorithm once, okay, you have a map, and then from every single intersection in the theme park, you know exactly where to go in order to get to the closest bathroom. Okay, so that's what this particular version of Dijkstra's algorithm can offer, as opposed to the standard Dijkstra's algorithm, where you have only one single destination and it only finds the shortest path from a particular vertex to the destination. So are we good so far with that, analogy? Okay. So with that said, I am going to use an example to illustrate this particular algorithm. So the example that I'm going to use is down here. It is actually in the lecture notes. I changed the A, B, C, D, E, F to numerical values 1 to 6 because there are some variables in the algorithm that might overlap with those particular letters. So that's why I changed the vertex names to just numbers instead of letters. So, do we have any questions about this graph? Okay, just don't ask me why there are certain lines that are thin and some lines are thicker. Okay, so for now, do we understand what this graph is representing? So all the arrows are arcs, or we can also call those edges. So we have an edge from 1 to 2, we have one edge from 2 back to 1, and then all the numbers along each edge would be the distance between the vertices. So if you are to go from vertex 1 to vertex 5, going through this particular edge, it will cost you 10 whatever unit. Okay, that's the distance. Are we good so far? Okay, so the idea is to find quote unquote the shortest path from every vertex to the closest destination. In this case, the two destinations are the ones with a double circle. So 5 is a destination, 6 is also a destination. So it doesn't matter which one you get to, as long as you get to a destination, we're good. So the destinations are equivalent to each other. Are we good so far? All right. So now the first thing we need to do is to represent this graph using a set notation. Okay, so we're going to do that first. So let me go ahead and start with that. Okay. I forgot my glasses, so I have to kind of squint to see stuff today. All right, so we'll start a new window. There we go. Can I put it over here? All right. All right. So what we'll do is we are going to start with E, the set E with an uppercase. That is the set of all the edges. So in this case, there are quite a few, but it's easy. So we can go in a very systematic way. We start with 1. So 1 can get to 2, 1 can get to 5, and that's it. Because vertex 1 has 2 outgoing edges, so that's it for 1. So now we look at number 2. So 2 can go to 5. 2 can go to 6 directly, and 2 can go back to 1. There we go. So 2 has 3 outgoing edges. Then we look at 3. 3 has 2 outgoing edges, 1 to 4, and then the other one to 6 directly. And then we look at 4. 4 has 2 outgoing edges. One go to 5, and then one goes to 6. And then we look at 5. 5 has no outgoing edges, and then 6 has one. So 6 has one outgoing edge to 4. So this is how we represent the edges in a graph as a set. Do we have any questions? Yes. I do not think so. Yep. This one attempts to find the shortest path. Yep. So I've neglected to talk about the set of all the vertices, but in this case, it's pretty easy. It's just 1, 2, 3, 4, 5, 6. Okay. You can use anything to identify a vertex. Okay. So there's no restriction whatsoever, whether you have to use letters, names, shapes, whatever, to identify each vertex. But once you identify the vertices, the edge set has to be a subset of the Cartesian product of V as a set with itself. So that one, there's a restriction to E based on what you choose for V. All right, so that's pretty easy. Now we look at the set of all the distances. So the set of distance is basically a map. It is a function where the set of edges is the domain, and then the codomain is going to be the set of real numbers that are non-negative. They can be zero, just not negative. So I'll be understanding what I just said because I just referred to some terms that we learned, what, 8, 9 weeks ago at least. Okay, so are we still comfortable with those terms? Okay, all right. So in this case, basically you just, okay, the laziest way to do this is to do this, okay? Because every single edge needs to map to a particular number. So if I just start with all the edges, that saves me some time. So now I can say, okay, what is the distance from, vertex 1 to vertex 2? So according to the graphical representation of the graph, it is a 5. And then I look at the next one, 1 to 5 is having a distance of 10, and then 2 to 5 has a distance of, okay, right, 2, and then 2 to 6 has a distance of 4, 2 to 1 has a distance of 4, and then 3 to 4 has a distance of, let me see, huh? Nope. Well, I mean, we don't know what scale we're talking about. We're not talking about actual distance. We're talking about, what is the cost, right? Huh? Oh, it's a 4, right? Okay, thank you. So 3 to 4 is a 4, and then 3 to 6 is an 8. There we go. So 3 to 6 is an 8, and then from is 4 to 5 is a 6. There we go. And then 4 to 6 is a 4 to 6 is a 2, and then 6 to 4 is also a 2. There we go. All right. So are we okay with the representation? The set of all the vertices is V, the set of all the edges is E, and then the set of, well, okay, the function is D, but it is a function that maps all the edges to a non-negative real number. I just so happen to choose all integers in this case, all natural numbers. All right, are we doing okay so far? All right, so with this representation, we don't need to look at the graph anymore. Okay, but for this class, I'm going to still kind of display the graph at a corner just so that we can see it. Some people are more visual, so when they look at the actual visual representation, it is easier for those people to understand. So I'm going to take a snapshot of this and then do the usual thing, make this always visible as I try to track down what is going on as we go through the algorithm. So I put it over here, and I'll put this one kind of over here. And okay, well, we'll see. All right. So okay, so this is a good time to kind of segue to your homework assignment. So I'll just kind of talk about the homework assignment a little bit because I also need to refer to a spreadsheet in the homework assignment. So now we go to your homework assignment, get this out of the way. So your homework assignment is not visible to you just yet. So I'm going to open it up right now. So now it is visible. The due date is December 1st, which is next Monday, I believe. Yep, it is next Monday. So you have 1 week to work on it. I don't think it's going to take you a whole week to work on it. Okay, after today's lecture, if you just kind of understand, if you understand the material from today's lecture and you have read the material by yourself, a little bit at least, it might take you half an hour, okay? Half an hour to an hour at the most. So that's due next Monday. But what I want to do is to borrow a link here because there's a link in the assignment. So in this case, you know, it it won't fit on this screen because I kind of zoom in and I have a fairly low resolution screen. When you use a regular browser, you should not, need to have to kind of slide the horizontal slider. So it's set up about the same way. You can see that you have a set of V, which are the vertices, a set of E, which are the edges, and a set of D, which are the distances. So set up pretty much the same way. So this is a Google Sheet that I want you to start with, or I need you to start with, okay? So we'll take a closer look at what it looks like. I'll make a duplicate of it for today's lecture. So we're going to go to make a copy, and we'll call this with today's date, 2025, 11/24. And app script file functionality will also be copied. Okay, that's fine. That's exactly how I want it. So you will be asked also, whether you agree to the permissions and whatnot. Just say yes. All right. So it is kind of cool because I'll show you why there are some scripts involved here and why it is actually kind of helpful. Because without that, it is much harder. All right, so to adapt it to this particular graph, I am going to change the boldface a little bit because I use boldface to indicate which ones are the destinations. So now we have 5 and 6 being the destination. So these two are now bold-faced, and then everything else is not bold-faced. All right, so this is the spreadsheet for tracing the algorithm. And then when we get back to the algorithm description itself, we want to look at this. Okay, so we're going to go back to the algorithm itself, which is right here. And I'll zoom back in because I zoomed out, just so that we can get a better view, or I can get a smaller view of the graph. So we are now zooming back in. There we go. So is that sufficiently zoomed in for people sitting in the back? Okay, all right. So we'll read the algorithm line by line, and you guys can tell me, if you have a question, just let me know. So the first line is, basically these are the input parameters or part of the input parameters. In this case, G is representing the whole graph. So G itself is a two tuple, which means we have two components to define a graph. The set of all the vertices and the set of all the edges. So we have those two defined earlier. Do we have any questions about this notation here? Okay. We also define the D, okay, which in this case, it is clear that it is a function where E, the set of E is the domain, and then the set of non-negative real numbers is the codomain. So are we okay with that? Okay, so that's exactly what we have defined so far. We also have a set S, okay, which is a subset of V where it contains all the destinations. So in this case, in this particular example, S would have two members. One member is 5 and the other member is 6. So are we clear on set S being the set of all the destinations? Okay. And then this is for initialization. So for each is not a declaration. This is a procedure. Okay, you can see it as a procedure. So we are basically saying for every vertex in S, L of V is going to be assigned a value of 0 because each destination vertex is at a length of 0 from a destination. So what we'll do is now we go back to the spreadsheet, and I have too many spreadsheets up. So we're going to have to close this one that we are not going to use, and then also close this one that we're not going to use. Close this one from last week. I just don't want to have additional stuff that is not going to be used. And there's an error. Internal error executing the custom function. I think it is supposed to ask me for permission of some kind. Mm, all right. All right, so we are going to go through some initialization. So the initialization says, everything that is a destination should have the L value, okay, which are the columns from column E to column J in the spreadsheet. So these two will be initialized to 0. So there's a 0 here. There's also a 0 here. So that's what row 3 is doing. Row 3 is going to look at the last row that has a definition for that particular column. So this way, it is easier for you to see the current value of each column. Because otherwise, if your spreadsheet is too long, you can easily lose track of the current value of something. I do not know why column Q is a little different because it really is set up the same way as all the other columns. So I am just going to change this a little bit and then change it back, see if that fixes the problem. You're trying to edit. Okay, fine. Okay, that fixes the problem. So I think it's a glitch that it had a problem before. Okay, there we go. All right, so that cleared the error. All right, so now we go back to the algorithm. So when you're doing this, it is really helpful if you have either a larger monitor or you can look at both at the same time. Um, Most people have a larger screen than, I mean, in terms of resolution, than what I have here. So you should be able to display both the spreadsheet and also the algorithm at the same time. All right, so the next one says for each V that is in V but not in S, we want to initialize every single one of those to infinity. The L value has to be initialized to infinity. So now we go back to the spreadsheet and do exactly that. So these are all infinity. So I'm just going to spell, INF for infinity. There we go. All right. So it is a good time to go back to the algorithm to explain, what does it mean? What is L value? What is the L value of vertex? So the best way to describe the L value of a vertex is it is the length of the currently known shortest path from a vertex to a destination. Let me say that one more time. Okay, the L value of a vertex is the length of the currently known shortest path to a destination. So the key is currently known, okay, which means it can change. So the reason why we initialize the way that we do is because we don't even know whether there is a path, whether the existence of a path from vertex one to either five or six at this point, because we're just starting out. So that's why from anything that is not a destination, the L value is initially infinity because it is representing that that particular vertex may not even reach a destination. So that's why they're initialized to infinity. For vertex 5 and 6, because they are destinations themselves, so the question is, okay, remember the second grader example? So you're standing right in front of the bathroom, and then one of the second grader asks, I need to go to the bathroom. Then just turn around and go like, it's right there. Okay, so the length of the shortest path from any destination to a destination is going to be zero because you're already at a destination. So is that concept okay? Okay, all right. All right, so moving on to the rest of the algorithm. So now we also want to initialize Q, which is set S. So in this case, Q is a set, and we are going to initialize it with two members. The two destinations in this case, in the example, would be 5 and 6. So that's how Q is going to be initialized. And you can also see how row 3 is reflecting the current value of the column, which is exactly what it is designed to do. All right, so we are now done with this one. E prime is interesting because E prime will always be a subset of E. It contains the edges that make up all the shortest paths from every vertex to a destination. That's the job of E prime is to keep track of quote unquote the solution edges, okay, or the edges that are on the shortest paths. And there's usually a certain characteristic to E prime when we are done. So we'll talk about that when we get to that point. But it is initialized to an empty set because we don't even know whether there is an existing path from any vertex to a destination. So it starts up with the most conservative estimate, which is, oh, maybe none of the vertex can reach a destination. So there's no such thing as a shortest path. So row 4 is representing the initialization or post-initialization of the algorithm. This is how we set up the data structures in order to proceed from this point. Do we have any questions about the current state of the program? Questions? Yes. Okay, so what do you want me to explain? Do you want me to explain the rationale, or do you want me to explain why the action of the algorithm initialize these to infinity? The reason why. Okay, so tell me again, what is L of a vertex? What is the L value of a vertex? Hmm? Nope. Just generally speaking, what is the shortest, the length of the shortest known path from that vertex to the closest destination? Okay. Yes. So how else do you think is a good way to initialize the L value? Not knowing anything about the graph, right? Because if we know anything about the graph, then we are done already. So we are this at this point we don't know anything about the path. Hmm? Yes, because we don't have any information. So the correct. So this is basically saying we don't even know whether there is a path to a destination cell from vertex 1, 2, 3, or 4. That's why L of 5 is a 0, L of 6 is also a 0. For anything that is itself not a destination, the L value is infinity. For anything that is a destination, the L value is 0 to begin with. Yes. If it is infinity, it means not reachable. It is not, it cannot reach a destination. And initially, we do not know anything about the graph, so we can only make that assumption that it is not reachable. All right. So are we good with the current configuration? Are we all okay with row 4 of the trace, this entire row here? Are we good with this? Okay, that's initialization. So if you want to, okay, for those of you with a computer right now, or you can do it later, is you can always make a copy of this particular spreadsheet. Just go to File, make a copy, and then you can annotate it any way you want. You can print it out. You add additional information per row. You can annotate. You can add your own comments. All right. So getting back to the algorithm. There we go. So now we get into the actual algorithm. So the actual algorithm is relatively short. It starts with this while and it ends over here. So with this notation, I'm basically saying, okay, it is kind of like Python, where the indentation tells you about the nesting. Okay, so now we have a few nesting level. We have while, we have these two that are not loops by themselves, and then we have a nested loop of a for each inside, and then inside the for each we have a conditional statement. So do we understand how to read the structure of the algorithm? So be good with that? Okay, all right, excellent. So the very first thing we notice is as long as Q is non-empty, we got stuff to do. Okay, we only terminate the loop when Q becomes empty. So that means for a graph that has no destination cells, we are done, which kind of makes sense, right? Okay, if a graph has no destination cells, then none of the vertex is going to have any path to a destination. So we are done. But in this case, we do have two destinations, so we are not done yet. The first thing we do, okay, so we want to kind of look at this statement here. So the first thing we do is select V as an element of Q such that blah, 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 okay? So this blah, blah, blah here is a condition, okay? We need to select a V such that this condition is satisfied. So if I hide the rest of the statement here, what do you think it is trying to say? So let's try to read this out, and in English form as much as possible. For every W in Q, we need to make sure that L of V, which is the one that we are selecting, is less than or equal to L of W. So what is that saying? You mean you didn't write any notes when I talk about that? Okay, go ahead. We are looking for the vertex that among all the vertices in Q, we want to select the one that has the shortest currently known uh, path to a destination, which is 0 right now because we have two vertices that both have the L value being 0. Okay, so the actual explanation, if I just kind of move this one aside, is we want to find the V that has the shortest length or the length that is the shortest to a destination of all the boundary vertices. So Q is basically a set of what I would call boundary vertices. Okay, are we doing okay so far? So this makes Dijkstra's algorithm a greedy algorithm. It is basically making the most optimistic choice, whenever it needs to make a selection. So that term, a greedy algorithm, will come back. Okay, after you transfer, it will come back. Basically, an greedy algorithm is at any point it has to make a decision, it will make the most optimistic choice. So I wouldn't call it greedy. Okay, I would call it most optimistic. Yep, yep. hmm It will eventually pick the correct one, but it can make the wrong decision first. Yep, but it will fix itself. Okay, it will fix itself. The only requirement is the distances cannot be negative. They can be 0, but they cannot go negative. All right, so are we okay with this particular sentence? We good? All right. So based on this particular sentence, and we want to apply that to the current state, what are we going to choose as V, given that the state is on row 3? Given that Q has two vertices, 5 and 6, and I want to choose the one that has the lowest L value. This is a trick question. So which one should I choose? It doesn't matter, right? Because they both have a value of 0. So none is actually smaller than the other one. They're both less than or equal to each other. So that means we can choose either one. So I'm going to let you guys choose. Which one do you want me to choose? Hmm? 5. Okay, so we can choose 5. So we choose V to be 5, and now we can proceed with the rest of the algorithm. So the rest of the algorithm, the first thing is once you choose something out of Q, you better make sure that it is not in Q anymore, okay? Because otherwise we end up with an infinite loop. So that means we're going to update the set Q so that 5 is no longer an element in Q. And you can do it on the same row if you want to, okay? You don't have to update your Q on the following row. This is fine because these two actions are really associated with each other. So there's no need to put them on separate rows because they're going to happen at the same time. All right, so moving on to the next step. So the next step is a little bit more complex, okay, because what we're doing is now we are looking at what I call a ad hoc set, where we say, okay, we need to choose all the vertices that end up at vertex V, which is chosen all the way up here, and make a set out of that. Okay, so we're looking at a set of edges, which is a subset of E, sorry, is a subset of E where each member of this particular set is going to contain edges that end up at V. So the way we apply this in the algorithm is to look at the algorithm here and we ask, okay, so what edges will lead us to V? And we're going to evaluate those one by one. So can you guys tell me what are the edges leading to vertex 5? There are, how many are those? Okay, so first of all, count. Okay, it is 3. Okay, when I saw your gesture of 3, I just kind of smiled because I was watching a movie where the one of the Nazis, yeah, Yes, yep, yep. Because the British spy hold up three fingers like this, but in Germany they do this. So that's how they could tell the British spy is not German. So that was just kind of funny. Yep, that's how my brain works. Getting distracted by my own self. Actually, getting distracted by my own memory, which is even better. So it's not even a sensation. It's not like, I'm getting some sensation. It's just my memory popping up. It's like, oh, wait, we watched a movie. All right. So there are three of them. Okay. So the way you explore the three edges that end up at vertex 5, the ordering is actually not important, even though it can give you, slightly different results later on, but it will still be correct. Okay. So once again, you have your choice. Okay. We got 1 5, we got 2 5, we got 4 5. How would you want to order those explorations? 1 2 5. Okay, so do you want 1 2 5, 1 5 2, 5 1 2, 2 5 1? There are six possible choices. Which way do you want? Hmm? Just 1 2 4? Okay, that's boring. 1 2 4. Okay, fine. Okay. So this is how I would do it, is I would list all the incoming edges to vertex 5 first, okay? This way I don't forget later on. Then I go back and then I look at, okay, let's look at the edge 1 5, okay? So the edge 1 5 is like this. And then we go back to the algorithm and we ask, what do we do with that edge 1 5? So we assume E is, basically in this case 1 5, W is the 1, V is the 5, and V was determined when we execute the select statement out here. All right. So the first thing we want to do is to compute what is L of V plus the distance of E, and E is, in this case, what, 1 5. All right, so getting back to the algorithm, getting back to the trace. So we are basically looking at, L of 5, which is a 0, and we want to add, the distance from 1 to 5, which is 10, which is basically 10, because 10 plus 0 is 10. And what are we comparing that with? We're comparing with L of W. So in this case, W is 1. So now we are basically comparing 10 against L of 1, and we're asking, is 10 less than infinity? What do you think? It is. Okay. So if that is the case, then we get into the then portion. It doesn't have an else. We only have a then portion. So the first thing we do is we update L of W. Okay. So we update L of W to become L of V plus D of E, which in this case means we are looking at L of V, which is a 0. We are looking at D of E, which is a 10. And then we use that to update L of W, which is L of 1 in this case. So that is now updated to a 10. Okay, and you can now see the magic of what row 3 is doing, because row 3 always updates based on the last update of that column. So that's why it is kind of cool. All right. All right. So now, because we get into the then portion, we also have to finish the block of statement. So the next thing we do is we remove all the edges, which is which is, let me see, we remove all the edges from vertex 1 to whatever from E prime. Okay, so we look at the E prime here. E prime has nothing in it right now. So when you remove things from an empty set, you just get the empty set back, which is fine. Okay. And what is the next thing that we need to do? We have to add 1 5 as an edge to E prime. So that's what we're going to do. So now so in the homework assignment, if you remove something, I need to use strike out to indicate that something is removed. But since we did not remove anything, there's nothing that we need to worry about in this case. And then the very last thing we need to do is to add W, which is 1, to the set of Q. So now Q has one more element. So we have 1 6 in the set of Q. So that concludes, so row 6 basically concludes the one iteration of the for each loop. The for each loop is right here. We just finished the first iteration. Do we have any questions about what that iteration did to the algorithm or to the trace? Hmm? Okay, so if you want to go to 1 6, that means v has to be 6, right? And didn't we choose v to be 5? Yes. Yep. What ordering of what? You mean comparing visiting 1, 2, or 4? That is correct. The ordering does not matter because I just asked you guys which way do you want me to proceed. Yes. Even though I cannot remember exactly what words I used, I can still remember the idea of what I said. Okay, so that's important. All right, so next iteration. Okay, the next iteration is going to look at the edge 2, 5. Okay, so the edge 2, 5 represented here. It has a distance of 2. So the question is 2 plus 0 less than infinity, which is here? Okay, so we're gonna go update it with exactly 2 over here. And then we have to now remove all the edges starting from vertex 2 from E prime. Well, there's none right now, so we don't have to remove anything. However, we also have to add the new edge from 2 to 5. So now we have 2, 5 added to E prime. And at the same time, we also need to add 2 to the set Q. So now the set Q has 1, 2, and 6 in it. Now we evaluate number 4, kind of the same deal. Okay, so 4, 5 as an edge is from here to here. It has a distance of 6. So now the question is 6 less than infinity, which is this infinity over here? The answer is yes. Okay, so we put a 6 here. And then we also have to go to the set of E prime, remove all the edges starting from vertex 4, and there's none. And then after that, we just add 4, 5 as an edge into E prime. And then we add 4 to the set of Q. So now set Q has 1, 2, 4, 6 in it. All right. Do we have any questions about the trays up to this point? Yes. No, no. Every step along the way, we're adding something. So after the first, for each iteration, it ends up with one edge. After the second iteration, it has two edges. After the third iteration, it now has three edges. Okay. Any other questions? Nope. Okay. So if there are no questions, then we move back to the algorithm. We are now done with the for each loop here because we have looked at all the incoming edges to vertex V. So now the loop goes all the way back to the outer loop condition, and we ask, is Q empty? Are we done? Not even close, right? Because Q now has four elements. Okay. So now we go into the body of the loop. The first thing we do is we select a vertex V in Q such that that particular element has the smallest L value compared to all of the other L values. So which one should we choose? So our candidates are 1, 2, 4, and 6. Of those four, which one has the smallest L value? Hmm? Not gonna say it. Okay. Number 6. That's right. Okay. So all you have to do is to look at this. 1, 2, 4, 6, right? One has an L value of 10, 2 has an L value of 2, and then 4 has an L value of 6, and then 6 has an L value of 0. I think 6 wins this time. Okay. So this time there's no tie because that's the only one with actually the smallest value. So we have no choice but to choose 6 over here. And then 6 is removed from the set. So we only have 1, 2, 4 left in the set. So now we want to enumerate all the incoming edges to vertex 6. There are three also. So we have number 3 going to 6. We have number 2 going to 6. We also have number 4 going to 6. So in what order do you want me to explore? Once again, there are 6 choices because 3 factorial is 6. So which order do you want me to do it? From lowest to highest? How about we just do it in reverse? Okay, we just did lowest to highest. So this time, how about we go from highest to lowest? Okay. So we are gonna go for 4, 3, and 2, right? Yep. So 4, 3, and 2. It doesn't really matter, okay? So this is one way for me to create variations in the final exam, okay? Because I can have a program to generate questions based on random order when they are supposed to be equivalent orders. Okay, so we'll start with 4. So what do? We look at this 4 and the 6. Okay, so in other words, this is where we're coming from. This is where we end up at. So we are looking at the edge from 4 to 6, which has a distance of 2. So what are we going to do? We have to add the L value of 6 plus the distance of the edge that we're considering, which is 2. So what is L of 6? L of 6 is 0. And the distance of the edge is, okay, I suppose I need to move my pointer a little bit. What is the distance of the edge? 2. So 2 plus 0 is 2. What are we comparing that to? We're comparing that to L of W. What is my current W? 4. What is L of 4 right now? 6. Is 2 less than 6? Okay, very good. 2 is less than 6. So we need to go into the then statement, which means we start with updating the 6 to a 2. So this time we got stuff to do here. Okay, so I'm going to copy and paste first. Okay, like so. And this time I go like, oh, we have to remove all the edges from 4 to whatever. So we do have one edge we have to remove now. Okay, so for Windows users, you use Alt Shift 5 to strike out, and then you have to add. Oh, okay, darn it. And then you have to add the new edge. The new edge is it keeps the strikeout. I'll fix that later. So the new edge is from 4 to 6. So let me unstrike out the new portion here. Alt Shift 5. There we go. All right. So let's go ahead and see what this actually means. Okay. Before, okay, we thought, okay, from vertex 4 to get to the closest destination, we should go to number 5. Okay. But now we just realized, guess what? There's actually a closer destination. It is number 6. So that's why we have to first update the L value because the new length of the shortest path from vertex 4 to the closest destination is no longer 6. It is now a 2. Yes, go ahead. What do you mean by I cannot go back? One, but that's why we have arrows. Would you want to shoot an arrow out of a bow backwards? Exactly. That's why we have arrows, okay? That's why this is called a digraph. The DI stands for directed, okay? This is a directed graph as opposed to an undirected graph. All right, cool. And we are not done with the updates yet because now we also want to say, hey, you know what? 4 is just updated here. So we're going to add 4 back to the set of Q. But since 4 is already in the set of Q, it is okay. Okay, it just looks exactly the same after the union operation. So that's the first iteration. The second iteration is to look at vertex 3 to vertex 6. So from 3 to 6, there's an edge of 8 over here. So this one is pretty easy because vertex 3 at this point still has an L value of infinity. So we know for sure that, okay, any known actual value is going to be less than infinity. So we're going to put the new value over here, which is 8. And then we're going to have to add the new edge, which is from 3 to 6. So copy and paste, add 3, 6 to the E prime, and then we also want to add 6 back to the, no, we add 3 to the set. Sorry, I misspoke. So now we have 1, 2, 3, 4 in the set. Are we good so far? Of the second for each loop iteration of the Dijkstra's algorithm. We good? Maybe. Okay. So there are a few things you need to think about when we do this. The first one is mechanical. Okay, can you follow the algorithm? Okay, if I give you the algorithm, can you perform the operations? That's the first one. And since all of you have at least taken CISP 360, because I checked your prerequisite, and you also must have taken or is taking CISP 430, I trust that you can read the algorithm and understand what to do. So that part is not the concern. The concern is, do you understand why we are doing it? So there's the two questions, what we're doing and why we are doing it. Okay. So when you do the homework assignment, I would say focus on the why. Okay. Why are we doing this? What does this do in order to find the shortest path from a vertex to the closest destination? All right, so we are done with the second iteration of the for each loop. Now we go for the third one, which is 2. Okay, so now the question is, what is the new, uh, from the perspective of vertex 2, did we find a shorter path? The length of the shortest path last time was 2, and the length of this new shorter path, the new path, no, I shouldn't say the new shorter path, the new path has a length of 4. So we did not find anything new, so that means there's no update. So the row 12 is just the way it is, with no updates to the L value, nor E prime, nor Q. Is that okay? Because the condition of the conditional statement is false. So there's nothing to do. Are we good with that? Okay, all right. So now we go back to the outer while loop, okay, and we ask, is Q empty? No, Q is not empty yet. So now once again, we have to find a vertex V in Q such that it has the smallest length, it has the shortest length to the closest destination. Okay, so who are our candidates? Our candidates would be 1, 2, 3, and 4. So we have these 4 values to consider. We have a tie of the lowest value, which is either the vertex 2 or vertex 4. So once again, you guys can choose which one do you want to explore first. 2. You guys are so predictable. Because in reality, it doesn't have to be vertex 2. If vertex 2 and vertex 4 both have an L value of 2, you can pick 4 first. Okay, it should not matter from the perspective of the correctness of the algorithm. With the trace change and the updates of E prime also change, potentially yes. Okay, but will it give you the wrong solution? The answer is no, it will not give you the wrong solution. Okay, fine, we will choose 2. So once we take 2, once we select 2, we have to get it out of the set queue, and now we have to look at all the incoming edges to vertex 2. So this is vertex 2, and it has one single incoming edge from vertex 1. Okay, so we just say 1. So now the question is, what is the current length of the shortest path from vertex 1 to a destination? It is 10, right? So what is the length of the shortest path if vertex 1 is to go through vertex 2 to the closest destination? So we go like, oh, okay, so let's check it out. L of 2 is only 2, and the distance from 1 to 2 is a 5. So that means the length of my new path, not necessarily shorter, but the new path has a length of 5 plus 2, which is a 7. So is 7 less than 10? Okay, well, if it is less than, then we have a bunch of stuff to update. So now we have to update here to basically indicate the length of the shortest known path up to this point is 7. Are we good? But in order to use that path, vertex 1 should not go to vertex 5 anymore. Instead, it should go to vertex 2. So that means in terms of E prime, we have to get rid of this 1, 5, and then we have to add 1, 2 instead. Okay, so now we copy and paste. Okay, so once again, copy, paste. And this time I'm a little bit smarter. I just add the new edge first, which is from 1 to 2. And then we go back and say, okay, 1 should not go to 5 anymore. Get rid of this one. So once again, Alt Shift 5. And on a Mac keyboard, there's another shortcut key combo to do the strikeout. If you want to learn what shortcut key you should be using based on your operating system, go to Format and then go to, hmm, where is it? Go to Text. Huh? Okay. Yeah, but if you use the menu, it will actually show you. It will tell you exactly what key combo you need to use. Okay. Because I know it's different compared to. Oh, you did? Okay, cool. Thank you. All right, but we are not done yet. Okay, because we found that we just updated the L value of 1, so that means we have to add 1 back to the set, but since already in the set, so it is not visible as an update, but you still have to update a queue to reflect that yes, we added we performed a set union operation, but it did not change the value of the set. But you still have to repeat the set to let me know that you need to update Q. It just turns out that the update, quote unquote update, is not really changing the value. All right, and that's it. Okay, because from vertex, um, there's only one incoming edge to vertex 2, which is coming from vertex 1. So we are done with that particular for each loop. So now we are going back to the outer loop, which is the while loop. Okay, we ask, is Q empty? Nope, it's not empty. So now we have to choose the vertex out of Q that has the least L value. So now we look at what is still in the set queue. It is 1, 3, and 4. So we are looking at 1, 3, and 4, and we are now asking which one has the shortest length to the closest destination. 4. Okay, so we don't have a choice in this case, so we have to say 4. And now we look into the incoming edges to vertex 4, and it has 2, right? Because it has one coming from 3, the other one coming from 6. So this time we'll go for increasing order. So we basically say to vertex 4, we have one coming from 3, and then the other one coming from 6. So now, whoops, I said 6. There we go. So now we go through the whole calculation again. Okay, so we look at the edge 3, 4. Okay, so this is the edge 3, 4. And we also look at L of 4. L of 4 is 2 at this point. So this is why I have row 3, because row 3 always tell you about the latest update, and that's why it is useful. So um, did we find a shorter path for vertex 3? The length of the shortest path of vertex 3 was 8. And I just found a path that has an edge of 4 plus the L value of 4, which is 2. 4 plus 2 is 6. So the question is 6 um, shorter than 8? Yep, it is. So that's why we have to update. So we put a 6 here because we just found a shorter path from vertex 3 to the closest destination. So that means a bunch of updates. Okay, so we look at this particular set. So the way I would do it, or the way I recommend you to do it, is to add the new edge first. The new edge is 3, 4, and then you go back and strike out the old edge that is starting with 3, which is 3, 6. So Alt Shift 5, strike that out. And then we have to add vertex uh, 3 to the set. But vertex 3 is still in the set. Okay, so that means it doesn't appear to have changed. Are we good so far? Because W is the one that we have to add back to the set. And in this case, W is 3. So are we good so far? Are we mapping the instruction to the actual update in the spreadsheet? Yes? Okay? No? Well, good thing we are still recording. Hmm? Okay. So if I'm displaying the spreadsheet, you can display the algorithm. So this way you can have one window to focus on the algorithm. Excellent. Okay. Very good. So now we move on to 6. Okay, we look at the vertex 6 to vertex 4. So we are now first asking, what is the length of the shortest path from vertex 6 to a destination? Yeah, it's a 0. So if it's a 0, and we know edges cannot have a distance that is less than 0, so that means for sure that we can just skip around because we cannot possibly have found a shorter path in this case. Does that make sense? Because vertex 6 is a destination itself. It already has an L value of 0. So it doesn't matter what you add to L of 6 at this point, it cannot possibly be less than 0 because all the edges have distances that are non-negative. Is that making any sense? Okay. But if you were to actually follow the algorithm and do the compare, it will still work out the same way. So we're not of, we don't have a problem there. And I just realized that I forgot one thing. Once I selected 4, I forgot to take it out. So now we have to go back and redo this part, okay? Because I'm supposed to take that out of the set. There we go. So we only have 2 elements left, which is 1 and 3. So out of those 2, which one is the smaller? So this is 1, this is 3. So vertex 3 is the one that has a shorter length to the closest destination. So we're going to have to choose the 3 here. Okay, not, not supposed to change that. Put the 3 here. All right, so incoming edges to number 3. It has no incoming edges. Okay, so that means we're done. Okay, but remember, I keep forgetting to take it out. Once we select 3 as a vertex 3, we have to take it out of Q. So now we only have one element left, which is 1. So we look at 1 and we look at all the incoming edges of 1. It has one single incoming edge, which is from 2 to 1. So we have to consider that. So now the question is, if I consider the edge 2, 1, does that mean vertex 2 has just found a shorter path to a destination or not? So first of all, we have to look up what is L of 2 right now. It is a 2, which means the length of the shortest known path has 2 units. Now we look at um, the L value of 1 plus the distance of the edge from 2 to 1. The L value of 1 itself is already a 7. So yeah, we kind of know that we cannot possibly have found a shorter path at this point. So that means this is all done. And I also have to remember to take 1 out of the set. So Q is empty at this point, but it's only after we explore the for each loop that we can conclude the loop. So now that we are done with the loop, this is what is left in E prime. So when you look at E prime, we have 2, 5. So here's 2, 5. We have 4, 6, and we have 4, 6 over here. We have 1, 2, and 1, 2 is right here. And then we have 3, 4, which is 3, 4 over here. So those boldface edges are basically E prime itself. That's our solution. Okay, are we at least getting a general understanding of how the algorithm works. Okay, so what are we supposed to do with E prime, right? I mean, this is supposed to be the the really useful, important map, taking all the second graders to Six Flags, right? So what are we going to do with it? So that means if you are on vertex 4, okay, and somebody asks, I need to go to the bathroom, okay, the closest way to the bathroom is go to vertex 6, which itself is a bathroom, okay? Or if you look at this graph here, if somebody, if you're on vertex 1 or whatever location is corresponding to vertex 1 in Six Flags, okay, the theme park, and somebody asks, I need to go to the bathroom, where are you going to go? You're supposed to go to vertex 2, and then once you get to vertex 2, you go to vertex 5. And then once you get to vertex 5, you're at the bathroom already, so you're all good. So that's how this algorithm is supposed to work. Yes. Well, vertex 3, not a problem. Go to vertex 4, and then once you get to vertex 4, go to vertex 6, and you're now at the bathroom. Yeah. So it's kind of cool, right? I mean, this is one single algorithm. You finish it, it finds the shortest path from every vertex to the closest destination, and you can have multiple destinations. The spreadsheet is a log of the action that we do when we execute the algorithm. Okay, so if anything, um, you need more time to really evaluate the whole thing. So there are quite a few pieces. So first of all, there's the graphical representation of the graph, okay? And then there's the algorithm here. And then there is also, the spreadsheet to keep track of the state of all the variables that are important in this algorithm. So there are different forms, of questions that I can make, to ask you about this. So I can give you guys, like an exam from the previous semester, so that you know what kind of question I can use. Okay. But the one that I give you is just going to be a sample, right? I can always come up with some other ways to ask questions about about Dijkstra's algorithm. There was a hand earlier. Yep. Go ahead. Say again. In 20 minutes? No, it's called Dijkstra's algorithm because a guy called Dijkstra made it. That's urban myth. But I did make the modified version. Okay, so the original version, which is what Iraj is going to teach, is not exactly the same one. This one is modified. So the modified algorithm has an interesting, since we have some time here, has an interesting origin. The origin of the modified Dijkstra's algorithm has to do with micromouse. So micromouse is is a robot, okay, which is supposed to navigate through a maze. So let me see if I can still have some UC Davis micromouse video that I can show you. Okay. Yeah, UC Davis does not compete anymore after I stopped teaching over there. Okay, let me rephrase. After they let me go because of financial limitations. And I will put financial limitations in double quotes because after they let go of all the lecturers, the full-time professors continue to get their merit increase every year. Yep. Huh? It's Micro Mouse. I taught the Micro Mouse class. Sorry? Oh, Mouseology. I see. All right. So I know for sure this is a UC Davis mouse. So we can go take a quick look. This is 2009. Oh, give me a second to change my audio output. I mean, there's really not much to hear, but oh, All right, so I think I need to kind of explain a little bit here. So let me explain. All right, so this is the robot. It is fully autonomous, which means it's not remotely controlled. It has no known configuration of the maze initially. So initially, there's no map of the entire maze. It has to explore, and while exploring, try to get to the destination, which is the center of the maze, as quickly as possible. Because that's the timing from the corner to the center is how we choose which team wins the competition. Is that okay? So when you see it, turning around, it's using a bunch of sensors to sense the walls. So it's basically mapping as it goes. So after it explores and discover a new wall, it has to update the map, and then it will run Dijkstra's algorithm in order to find out, okay, if I need to go to the center, what is the closest way, what is the quickest way to get to the center? Um, in this particular class, I think for that year, everybody made, designed, fabricated, and soldered and debugged their own circuit board. So all the printed circuit boards were custom. Um, they use the AVR chipset in those particular circuit boards. So the AVR chip they use was a big brother of the um, Arduinos. So Arduinos use basically the same chip, but the chip that my students use are kind of like a beefier version of the ones on the Arduino boards. Many of my students also use my real-time kernel, which allows multi-threading, in on that particular circuit board. They also have to write the program. I did not provide any libraries. Okay, so basically all they have is a C compiler. Um, I don't give them Dijkstra's algorithm. They have to implement Dijkstra's algorithm. They have to do all the motion control software. Okay, so they have to know how to accelerate, how to decelerate, how to turn, how to correct based on the distance to the walls, and so on. They also design their own chassis. So the chassis design depends on which team you're talking about. I think one year, excuse me, I had a whole team of computer science people. Computer science people do not do much mechanical work. So what they did was they went to not HSC, they went to Tap Plastics, okay, which is right around the corner here. They went there, they bought a bunch of acrylic plastic. Well, okay, I take it back. They did not buy anything. They asked for donation. They went to the they went to the scrap bin and go like, oh, can we have some of this, which is not of any use to Tap Plastics, and they got a bunch. So they went home, they cut, they scored, they cut, and so on, and then they hot glued everything. Hot glue, yes. So not a whole lot of precision parts there. They hot glued everything, and then they wrote the software. The day before the competition, somebody accidentally dropped the robot, and the plexiglass just shattered. So you would think, oh man, this team is not gonna make it. Nope. All they did was to remake another chassis, hot glue everything back together, and they won the competition the following day. So their magic is software. Okay, they accounted for every possible way that the robot can misread something, can veer off, can have any type of mechanical error. They corrected everything that is possible, and that's why they won the competition on the following day. And then you also have teams with people with mechanical engineering skills. So they would do all the CAD stuff, actually mill a robot chassis out of a solid block of aluminum. So the robots vary from one team to another team. Some teams would use a stepper motor, which is the easiest kind of motor for this kind of application. Other teams have tried to use um, three-phase. Okay, what is the name of that thing? Brushless. That's it. Three-phase brushless motors. Now that is truly impressive because the three-phase brushless motors, which are the same kind that you find on drones and most of the power tools, they were not designed for precision control, motion. And those teams, were able to figure out, how to post width modulate the relative power of the three faces in order to do precise motion control. Okay, and so that was kind of impressive. Okay, some of those teams are really impressive. So that's what we did, and this is the first time I ran into Dijkstra's algorithm. And the thing about this thing is, it only has, I think it has 64 kilobytes of program space and about 2 kilobytes of RAM space. So your stack and all the global variables, they all have to fit in 2 kilobytes. So you cannot really have elaborate data structures. Okay, you cannot just say, "Oh, I'm going to implement a set like JavaScript." No, you cannot do that. You cannot just say like, I'm going to use the template class set in C++. Nope, you cannot do it because the moment you bring in a template class like that, your code is going to exceed the entire memory of the chip just because of the set template class. Okay, so they had to save memory as much as possible and do single bit representation of the walls. So that was a lot of fun when I taught that class. Yep. Nope, it does not use a camera. It has so this particular one has a distance sensor. It sends out an IR beam, and but it's not time of flight, so it's not a lidar. It is a much simpler mechanism. So it uses triangulation. The way it works is you have a device, okay? It has two lenses, okay? One is just you're shooting out a narrow beam of IR, and then the reflection comes back, and then the sensor on the other side is a linear sensor. So it can tell, which spot on the sensor is seeing the reflection. So you basically use triangulation to figure out the distance to the object. The other lens captures the reflection, which hopefully is still a small beam enough that you can tell the distance. Yep. And then they have to use the ADC or the ADAC on the controller to perform analog to digital conversion, and then use a map to map the analog value back to the distance that the analog value is representing. That's how they can tell the distance. Yep. So when UC Davis was still in the game, we held the tie record with the University of Hawaii of the most wins, in the history of micromouse. But UC Davis had the longest streak, so we actually edged out, the University of Hawaii in terms of the most winning team at the time. Yes. Oh no no, Waymo is way more complicated than this. This is really simple. Yeah, this is really simple because remember we are using those tiny little MCUs or microcontroller units, only with about 64 kilobytes of program space and about 2 kilobytes of RAM space. So all the data structure has to fit in. Guess what? Roomba would be closer. Yes. Yeah, Roomba would be closer. But the point of these exercise is, is a product design class. It lasts 3 quarters. It starts with fall, and then winter, and then spring. So it's a 3 quarter class. It lasts basically a whole academic year. Yep. But they don't do that anymore. As soon as I quit, they stop all the micro mouse activity because it's actually a really hard class to teach because you have whoever is teaching the class needs to understand mechanical design, electronics, circuit board design, programming, algorithms, how to diagnose every single possible problem that you can end up with. Um, but it's a lot of fun. Okay, I have to teach my students how to do surface mount soldering using a regular soldering station. And I have techniques. Okay, I got techniques, where people can do actually, pretty high density surface mount soldering. Oh, we got techniques for that too. No, 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 no. You don't have to. So the key, okay, so this we only got about a few seconds left. So the key to desoldering is counterintuitive, or you can call it paradoxical, is to put a lot of solder onto the board. So this way you have enough thermal mass, so it stays molten for longer, for just long enough for you to use a pair of tweezers to go like take it off. And cleaning up is not that hard because you can have the tissue equivalence in soldering is called hmm? Yeah, it's called desoldering wick, WICK. Yep. Yes, it does suck. That's its job. Yes, that is its job. Yep. Yep, they do because that's tech ed. That well, they changed the name to what manufacturing and blah 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 something. But anyway, they do have an electronic lab. Okay, so if you take ET classes or electronic technology classes, they have classes that can teach you how to kind of make simple circuits and also how to solder and stuff like that. Oh, that's not useful for something like this. Yeah, because this has really really high precision parts. Yep. Hmm? Well, I try to do that at ARC, but generally speaking, we don't have enough students with an interest. So that's why I started a class. I actually had classes already planned, but because of low enrollment, those classes never took off. Yep. Yeah, well, it's okay. I mean, I understand, this is a community college. It's a little bit different, but yeah, it was fun when it lasted. All right, I'll see you guys on Wednesday. Yes, we have class on Wednesday.